So I have two screens, so hopefully I can see all your faces in the other screen while I'm presenting. I thought it's always easier to use Zoom, but I don't think so. I always like in-person meeting, but due to the weather, I decided to make this online. So just for your safety, I don't want you to rush, try to catch the transportation. Hopefully, this is a different experience for today. We will see which one is better. The bad thing, you will miss the chocolate and protein bar as usual, but hopefully next lecture, I'm going to compensate for that. Maybe I can give double number and so on. All right, so for today, as we discuss, we will go over logic gates, and at the end of the class, feel free to stay. We are going to have it as office hour, although my office is always open for you, so you can come up, show up anytime, you can ask questions and so on. But I would like to encourage you to use the office hour, so let's have it after the class. Feel free to stay, ask questions. If you don't have the time, or if you have another class, just feel free to ask over email, or just come to my office right after the lectures on Monday and Wednesday. This is the right time to ask questions, basically. All right, so good morning. I hope you are warm. I hope you are in safe place and everything was good with the last two storms. And for today, it's a very interesting topic. Finally, we are moving from the data layer in the compute stack. We are moving to something that we call digital logic or logic circuits. So this is a very important topic. We are still going over these three books. As we said, the one to the left is our reference, the main reference, but feel free to visit the one to the right, which is the most updated one, and you will see more useful stuff. And for most of our slides, I'm trying to use some of the slides from the book or from the author of the book themselves. They are very valuable resource, and I would like to acknowledge that. This is the last lecture on chapter 1. So by the end of this lecture, we already finished chapter 1. If you prefer to read from the book, hopefully you are orchestrating or synchronizing with us. And there are a lot of valuable questions by end of each chapter or each section. So feel free to go over these. The solution to these questions is already posted online. So you can see all those questions, answer, if you'd like to check the correctness of your answer and so on. If you have any questions about those, or in case like you couldn't know how to answer them, feel free to ask. All right. So this is our story. We will repeat this several times throughout the course. This is what we call, again, as a compute stack. And this is extremely important aspect in computer architecture. Why we call it compute stack? Because every time you want to do any kind of computation, you have to go through all these layers of stack, okay? So starting from the very first layer at the top, you start to interact with the computer, with the software, and you have to pass through all these layers in order to get your computation done. And this is another expanded view of that compute stack. There are two extremely important research papers. The first one called "There is plenty of room at the top," which means at the top of the compute stack. But this paper tried to handle the things at the software level. There is also another important paper at the bottom, says there is plenty of room at the bottom. And the bottom we means here the bottom of the compute stack, which is the hardware. So these two papers try to tackle those two aspects, which is the software and the hardware. And normally we co-design both of them together. We don't separate them. And that's why we try to clear the misconception in the beginning, saying that computer architecture is not really a hardware, it's not really a software, it's really a mix or co-design, cooperation between these two concepts. We moved already from the data layer at the top, and now currently we are at the logic layer in that compute stack. So hopefully with the previous 4 lectures, we understand how data are stored in computers. And currently we would like to know how we perform operation on those numbers or on those data that we already format or represent as a binary, hexadecimal, decimal, and all these representations. And for that, we would like to visit the first topic called logical functionality. Logical functionality. And it really makes sense to call it as a logic, because we will see that always we answer as yes or no based on the logic-induced functionality. So how many of you know any type of logic gate that can perform computation? I already give you the answer, but I would like to hear from you what those logic gates that you are aware of.
There's and, not, nor, NAND, nor,
Don't read.
XOR.
Don't read, please.
Oh, I'm not reading.
Excellent. Perfect. Perfect.
But yeah.
What else do you know? Yeah, that was amazing, actually. So all of those gates, we call them logic gates. They are basically performing operation on binary. So we have to really get the binary data in order to perform this computation. So if your data is in hexadecimal or decimal, always convert into binary, and then you will be able to perform this computation. And you will see different functionality with those, and a combination of those gates will result in a complex computation. So even if you think like this is very simple operation like AND, OR, XOR, and all of these, like how we could achieve, for example, statistical analysis with really much complex operation. And you will be surprised that most of the computation around the world can be made out of those logic gates. And we will see a few examples. We will quickly cover these gates. Hopefully, you're all aware about the functionality of those gates, but this is just as a recap or just a refresh for all these ideas, because we are going to use them very often in our processor. And there is kind of almost impossible to have a processor without support of these logic gates. The first one, and the easiest, is what we call as a buffer. And buffer is doing nothing, basically. So whatever you pass to it, it's going to give you the same value as output. The only functionality that we use it for is to reconstruct the signal. What does that mean? It means whenever we transmit data from one place to another, there is some kind of distortion or noise happening to that signal. Sometimes it could cause a value of 1 to be a 0 just because of that noise. And the functionality of the buffer is to reconstruct that. For example, if we get a noisy input up to some extent, the output would be reformed in a correct way. So we will get a perfect one, for example. Of course, there is no perfect. There's always variation with the industry or with the component, but we will get much better shape for the signal of value 1. Likewise with the 0. And that's the only functionality we have with the buffer gate. The second similar or very simple gate called the NUT, and the NUT is basically inverter. So if we have a 1, it will be converted to 0. If we have a 0, it will be converted to 1. So now let's build what we call as a truth table. Truth table is basically just a representation for the input and output. So now if we go with the NUT, whenever we have a 0 as input, we'll have as a 1 as output. Whenever we have a 1, we'll have a 0 as output. In the buffer, it's exactly the same. Whatever the value is, we'll have it as output. Whenever it's 0, it's 0. Whenever it's 1, it remains as 1. Now let's move just one step ahead. Now there is another gate called AND is basically as a multiplication. So you multiply a bit of value 1 with another bit of value 1, for example. 1 times 1 is always 1. But whenever we have a 0 in any of the two inputs, the 0 always dominates, because this is like multiplication. So 0 times anything is 0, right? So likewise in here in AND gate. So always the 0 will dominate. So whenever we have 0 in any of the two input, it doesn't matter how many input. You could have like 16 input gate, okay? It's like 16, all of them go to one output. And whenever we have 0 in any of them, the output will always be 0. So let's build the truth table with the AND. Whenever we have a 0, doesn't matter how many of those zeros, any single 0 directly result in a 0. A 0 result in a 0, a 0 always lead to a 0, and here we have no zeros, so 1 times 1 is always 1. As simple as that. It's extremely straightforward. Now, when we have an OR gate, OR is like addition. So when you have a 1 in any of the input, the output is always 1. Whenever we have 1 in any of the input, the output is always 1. Let's see. Now, when we have a 0 and 0, 0 or 0, we don't have any 1, so the result is
0.
Perfect. The result is directly 0. Now, we have a 1, so the output should be 1. We have a 1, the output is 1. We have two 1s, doesn't matter how many 1s you have, at least we need 1. If you have a 1, directly the output is 1. As easy as that. You could always replicate, increase the number of input. There are a lot of gates with like 8 input, 5 input, 4 input, and so on. And it really depends on the functionality that you are using. How many of you use something called FPGA? Field Programmable Gate Array. This is like hardware device, small kit, like a remote controller for a TV, for example, very small device. You connect to your PC through USB port or something more advanced like PCI Express, and then you can program a logic gate inside that kit. And there is like very cheap one, like $20, or very expensive one, like $20,000 as the most advanced ones. And normally we have millions of those gates on those FPGA. And the FPGA is different from CMOS or a chip. In the chip, the circuit is already fabricated. It's already designed. You cannot change it. In FPGA, you can do whatever you want. All the gates are there, and you can program them to make a function or a circuit out of it. Every time you think about, oh, now I finished this project, let's move to another project, you just reuse that FPGA. You don't need to throw it away and fabricate a new chip as in CMOS. All right, now let's go to another level. Now we start increasing the complexity. I'm sure that you're already aware about all of those gates, but we really need to recap because we have a loose requirement for this course. Not everyone already studied those. So for the first gate, we call it XOR, and you can see OR is common. That's why we have this curvy shape over there that represent the OR. However, we have a double of that curve to represent the XOR, and this is how we really draw it. Now, XOR, I will tell you very simple rule that you can use it regardless the number of input. It doesn't matter how many inputs you have there. Hopefully, you can see my cursor on the screen. Can you see it, everyone?
We can see. We can.
Yeah.
All right, amazing.
It
Now,
would be great if it can be a red pointer, maybe if possible. The other pointer options.
we could go for laser. Okay.
Yeah, that is correct. Yeah, perfect.
All right. So it doesn't matter how many input we have for the XOR gate. If the number of 1 is odd, if the number of 1s in the input is odd, the output is 1. Whenever the number of 1 in the input is odd, not even, then the output is 1. As simple as that. It doesn't matter how many input you have. That's the only rule that you can use. Let's see an example. So let's build the truth table for the XOR. Remember, always truth table means input to the one side, output to the other side, and you have a vertical line separating both of them. All right, so in the first case, we have 0, 0. Do we have any 1? No. What is the output? 0. The second case, we have 0 and 1. Do we have 1s? Yes. How many of them? Only one. Is 1 odd or even? Odd number, right? Then we directly have 1. Okay? The third case, 1 and 0. How many ones? Only 1. Is it odd or even number? Is odd, right? Then it's 1. Now in the final case, we have 1, 1. How many ones do we have? We have 2. Is 2 even or odd number? Is even. Not odd, then it should be 0. As simple as that. You don't have to remember the table, because I might ask you in one of the quizzes for 3 input circuit. Then good luck. If you remember this truth table, you'll get lost. I'm always trying to emphasize in this course to rethink why we design it this way. If you remember this, it's very easy for you to solve any kind of problem related to this. Any question on this? Amazing. All right, let's move to something we call NAND. NAND. So NAND is basically an AND gate, but the output is inverted. The output is inverted. So you can split it into 2 gates as AND followed by NOT gate. NOT gate. So in this NAND, we have the input on one side, we have the output on the other side. Let's build the truth table. Remember, this is a multiplication, and then you just need to invert the output. For example, we said the 0 in the multiplication will dominate all the time. So whenever we have 0 in any of the input, the output is always 0. So now 0 times 0 is 0. Now flip the output from 0 to be 1. Let's see. Yes. Now the second case, 0 and 1. 0 times 1, again, 0 will dominate, so the output is 0. Let's flip it into 1. Don't forget the flip. Whenever you see this little bubble or a circle, that means an inverted. And those are standard gates. However, you could play with them. So for example, the A over here, you can still add, and let's change it into a pen. You could add a bubble over here. You could also add a bubble over there. You could remove the bubble from the output, right? So you could really play with this circuit. However, this doesn't change the functionality of this gate. To remain as AND, you are only playing with the input and output, to flip it or to not flip, okay? So be careful with that in any quiz or the exam questions that we might ask. All right, now let's assume, let's go back. The laser, let's assume we have this circuit as originally, nothing changed, no change in the bubbles. Now when we have 0 and 1, 0 times 1, directly 0, 0 will dominate, the output is 0, and we flip into 1. 1 and 0, exact same story. Whenever we have 0, doesn't matter how many zeros, even if single 0 directly dominate. And then we flip into 1. Now when we have 1 times 1 is 1, but we flip, and the output will be 0. Okay? Now the third case, which is exactly the same story, however, we just replace the AND with the OR gate. So we have OR means addition, so the 1 will dominate. Whenever we have 1, doesn't matter how many of those ones, whenever we have any one, directly dominate. So when we have a 0, 0, 0 plus 0 is 0, and we have a NOT gate at the output, so we flip the output. So it will be 1. Now when we have 0 nor 1, then 1 dominate, the output will be 1, and we flip into 0. Likewise, same story with 1 and 0. 1 will dominate, the output is 1, we flip into 0. Now 1, 1, 1 will dominate, doesn't matter how many ones. We have 2 ones, 3 ones, 4 ones, same story, the output is always 1, and we flip into 0. As easy as that. Okay? Now let's go to the XNOR. Remember, the XOR is this shape, and we don't call it N XOR, we call it XNOR. which is the same thing, okay? So we have an XOR and a NOT gate at the output. Very simple, okay? Now, do you remember the rule for the XOR? This is one of the fundamental gates. You just need to remember that rule. Yes, go ahead, please, Alex.
As long as the number of ones is odd, it'll be 1.
Excellent, perfect. That's for XOR. Remember, this is XNOR. You just need to flip the output. If it is 1, 0, if it is 0, 1. As simple as that. If you always follow the way I explain it, I guarantee you, you will make no mistakes, no confusion in these gates. All right, so let's build the truth table. We have 0, 0. Any ones? No. So what is the output?
0, but it's negative, so you'll flip it, or yeah, you'll flip it to 1.
Let's see. Excellent. All right, second case. Any ones? We have 1, 1. Is it odd or even? Single 1 is odd number, right? So the output is 1. We flip, becomes 0. Likewise, same story in the next case. So 1 and 0. We have single 1, it's odd number. The output is 1. We flip into 0. And we have 1, 1. It's an even number because 2 ones now we have. So the output is 0. We flip into 1. As easy as that. Right? Any question? Yeah, hopefully that was an easy meal in the morning. Unlike the previous quiz, there were people like spending a very long time on that quiz. I don't know why. We will see at the end of the lecture. All right. I see more people joining. Please admit them. Let's see another case of NOR, but now with 3 inputs. It doesn't matter how many inputs we have. The rules that I mentioned, I try to generalize them from the beginning. So don't feel like, oh, confused now, we have more inputs. No, it's exact same story. And there is one point that I didn't mention, but I assume like all of you are aware of, how we build the truth table, how you permute the input, how you build all kind of permutation for this input. So you always list the input from left to right in the same order they are mentioned in the exam question or in any kind of problem that you're trying to design. So if I tell you the input are A, B, C, you list them in the same order, okay? And then you go from the rightmost side, for example, C, whatever the last input is, and then you try to always permute as 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, okay? The second one, 2 zeros, 2 ones, 2 zeros, 2 ones, and then 4 zeros, 4 ones, 4 zeros, 4 ones, and then 8 zeros, 8 ones, 16 zeros, 16 ones. You can see the pattern. Now we are playing with the base to the power of something in the binary. So do you remember the number we listed last time? 1, 2, 4, 8, 16, 32, 64, and all these numbers, right? Those are the available value of each digit in binary system. That's the exact number that we are going to use over here. So we have here 1 0, 2 zeros, 4 zeros, 8 zeros, 16 zeros, and so on. Okay?
Excuse me, Professor.
Yes. Go ahead. This is
If
Hamza.
I'm not mistaken, normally in a truth table, doesn't it usually start with true and then alternating with false, meaning like 1, then 0?
No, we always start, it's logic, right? So we always start from the minimum value, which is 0, right? So all of those together should be added up to 0. All of these. You see this value, this entire value is all zeros. And this makes sense. This is how we count, right? So we start permutation from 0 all the way to all ones. So the last line should be all ones. And the first line should be all zeros. So you could, for example, have that in decimal, like 0, 1, 2, 3, 4, 5, 6, 7, all the way until you get the maximum value out of these number of bits, and then convert that into binary, like 0, 0, 0, 0, 0, 1, 0, 1, 0, which is 2, and then 3, then 4. If you see this pattern, we can use a pen here. Yeah, if you see this, for example, what is this in decimal? Directly you say 1, 2, 4, and then you see where are the ones. So 4 plus 2, that is 6, right? And this is the last value is 7 because we have only 3 input that we can build as 3 bits value. And the maximum we can have for 3-bit value is 7. So we always start from 0 over here all the way to the 7 over here. If we have 4 input, the same story, we'll start from 0 all the time. The first row should be 0. The last row should be all ones. If we have 4 input, then all ones, whatever this value is in decimal. So this in decimal is 1, 2, 4, 8. What's that in decimal? Actually, there is another way. You don't need to convert this into decimal. You don't need to say like 1 plus 2 plus 4 plus 8. You just go 1 digit extra, which is 16. And then the addition of all of those should be 16. As simple as that. Or you can say 8 plus 2 is 10, plus 4 plus 1 is, 15. 15, which is this number minus 1. That would be the result of the addition of all these ones. But this is how we build the truth table. We start always from 0. The last row should be all ones. Now, of course, it doesn't matter this order. You can play with it because at the end you are considering all permutation. So you can start with all ones in the beginning. You can start from any random number over here, but that will create a lot of confusion and you might miss a lot of entries. To make the things more organized, to not miss any of these rows, I really recommend everyone to start all the time from 0 and end with all ones, and then permute every time you just add 1. So from 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, just add 1. There are people who like memorizing. So if you would like to memorize, just go with the first column, permute from 0, 1, 0, 1, 0, 1, 0, 1. Then here 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, 4 ones, 4 zeros, 4 ones. Keep doing that until you arrive to the last row as all ones. Then you need to stop. If you have a 4th input, do the same thing. 8 zeros, 8 ones, 8 zeros, 8 ones. Is that clear, all the confusion? Hamza?
Yeah, that's clear. Thank you.
All right, perfect. Yeah, please feel free to stop me anytime. I'd like really to see interaction. Feel free to ask questions. All right, now let's see NOR. NOR is basically just OR gate, and we invert the output. So again, we start from all zeros. In OR, just addition. If you add 0 to 0 to 0, that's still 0, but we invert the output, so the output will be 1. I know most of the time you forget the bubble at the input or the output, so just pay attention to that. There is no rule on that. You just need to pay attention. That's the only thing you can do. Remember, the bubble can be at the input side, can be at the output side, can be at the all inputs, can be at none of them, can be in one of them, few of them. Just pay attention to that. Now, when we have 0 plus 0 plus 1, the output is 1. We invert it, it becomes 0. Then same story next. Next, we have 1. We have 2 ones, actually. So the 1 always dominates. So the output is 1. And we invert it or flip, then the output is 0. Same story here. Same story here. We have 2 ones. 1 will dominate. Output is 1. We flip, becomes 0. Now in 3 ones or all ones, the output is 1 because it doesn't matter how many input we have. Whenever we have any 1, it directly dominates. And then the output is 1, and we flip, it becomes 0. All right, so now let's go to AND with 3 input, exactly same story. So I'm going to skip this. I'm going to show it quickly. Whenever we have 0, just 0. There is no bubble at the output, so it doesn't matter. We are not flipping the output. Whenever we have all ones, because 0 will dominate, whenever we have any 0, directly the output is 0. So here we have 1, done. All right. This is another way of how we can represent all these gates. So you see this representation. This is cartoon representation. In real life, you might have this representation on one of the software. So there are a lot of software, especially if you are dealing with FPGA. You can use like, for example, Intel FPGA. You can use AMD FPGA, and so on. In their software, you can drag drop those gates from a library. So you will see this exact shape in a library, and you just drag drop to the drawing sheet, and then you start connecting the input to the output, and then you can simulate this gate. And if you are really interested into this, I can send you a few links to the software that you can use to simulate these gates. So this is one of the representation to draw these circuits, which is we call graphical representation. However, you can do that in code as well, which a language that we call system Verilog. There is a Verilog language, and there is a system Verilog. System Verilog is a bit easier in terms of representing the input and output. You don't care about the data type. You just say something as to replace or to represent that data type. So, for example, you can see here the name of the gate that you are using, and then just an instance name, which is like a name of the function that you are using. For example, you are using NOT, and the G1 will be the name of that instance. So you can refer to that gate later on, because you could use like 10 NOT gate. So you need to give a name to each of them so that you know which is which. Over here, you will see the output first. Always the outputs are first, and then followed by the input. Followed by the input. Okay. Now, if you want to connect the NOT to something else, you would just get the output of this to the input of the next. Like if you write instead of A over here as Y1, then you are connecting the NOT to the input of the AND gate. As simple as that. And then you can think about whatever you would like to build over here. So you just need to play with the position of this. You need to respect that position, because really this is the output, and this output is ordered. So if you have multiple output, you need to respect that order. Or there is another representation. I don't want to go through this in detail, but there is another representation. If you don't want to respect the order of those parameters, you can use dot and then the name of the port. For example, if you are always referring to the first output, you can call it Y1, then parentheses, and then give it whatever name you would like to have. In this way, you could have this really last item in the parentheses. It doesn't matter where you place these parameters, because now with using this way, you are always saying take whatever between the parentheses and map it to this output. Okay, in this way, you don't need to respect the order of those parameters in the function call. But if you don't want to go through these details, just follow this, the output first, and then all the inputs after that. Okay, and this is the name of the gate. You cannot come up with your own name. This is really should be something from the library itself, which are the logic function themselves. And this is your name. This is, you can call it whatever you want, just an instance name. Right? This is the interface, how many input you have, how many output, right? Again, as I said, in system Verilog, things are easier in terms of the definition of the data type. Here, you just call it logic. You really don't need to define what is it inside exactly, how many bits and so on. You just need to say logic, done. And here, the end of module, okay? And you have, remember, semicolons over there at the end of each line. Right? Again, if you're interested in how you simulate these kind of code or the graphical representation, I can send you a few links to the software that you can use to do this. All right, it's clear. Let's go back to the laser and move on. All right, now this topic is really interesting, and I already mentioned a few of it in the beginning of the lecture when we explain about the buffer the buffer. Now, there is something called logic level. Logic level. This is extremely important topic in order to go to real life example. We have the book, we have theoretical things in the book, but when we go to real life, you'll see something different. And then you'll have that maybe cultural shock or maybe education shock, like I was using these logic gates, I always sending 1 or 0, but now in real circuit, I don't have 1 and 0. I have something else. Let's see what happened in real life. Do you remember this slide? This is from the 3rd lecture when we talk about transistors. We said, what is the point of having the binary number system? Is that we build the computer out of transistors. Transistors understand nothing except 1 and 0. Either you activate the transistor or you disable the transistor. And that's why we invent the binary system. There is always a purpose behind anything we do in life. And that's the purpose why we build the binary system. All right, so to enable a transistor, you need to provide a VDD or a high voltage. A VDD or a high voltage. Okay? In order to disable, you just connect it to ground, which is a low voltage. Now in binary, we cannot represent high or low. We don't care if it is high or low. We just care about whether it's 0 or 1. Now we said a 1 is not really a 1. A 1 in computer system is something else. And that really depends on where you are locating that 1. You could have that 1 located in the main memory, in the DRAM. Then the 1 over there is different than the 1 in the processor. Is different than the 1 in the cache. Different than the 1 in the SSD, in the storage system. So it really depends on the location of that 1. This is how we can define the value of that high voltage. And this is power supply. We discussed last time that the power supply provides multiple voltage levels. It's not single voltage level. It's multiple of them. And it really depends on the component that are connected to that power supply. In this example, we have 3 voltage levels. We have 5, 3.3, and 12. You can see there is a positive and negative because sometimes we have differential circuit that operate on 2 voltages in the same value, but some of them positive, the other one should be negative. That's what we call differential circuit. But we don't have to go through this detail. You just need to know that the voltage level over there, we have 3 levels because we have multiple components that rely on different voltages. All right. Now, we made the abstraction for the high level or the voltage level, and doesn't matter whatever that voltage is, we always convert into 1. However, there is something that we call as a voltage drop. Voltage drop. So even if we have 3.3 as a volt, okay, at the receiver side, when we transmit that 1 from one component to another, we might see that value is dropping. Instead of 3.3, becomes 2 volt. Now, what is the threshold for us to consider that value as a 1? Do we need to require strictly 3.3 to be 1? And if it is less than that, then it's directly 0? Let's see. One of the reasons why we drop or why that voltage drops is something we call as resistance, a resistance. And this resistance, you can think about it as the component, the hardware component. We have component called resistor, okay? And we have capacitor, we have light, for example, we have many other components that you connect to your circuit. So you could think about it as a resistor, which is the component, the physical component that you can purchase, a resistor, right? Or you can think about it as any physical element that you use to conduct electrical signal. For example, a wire. A wire has a resistance. So a physical wire could be metal, could be copper, could be anything, right? It really can conduct or transmit electrical signal through it. However, those wires have their own resistance. And that resistance in a wire goes to distort or add a noise to the transmitted value. Okay, that's one of the examples. And we define the resistance as opposing the flow of electric current. And if you go to the physics, the reason behind it is really physics, because the atoms of the electrical signal that you are sending will collide with the atoms of the material itself. So if it is metal, then the atoms of the metal will try to collide with the electrical signal passing through this wire. And likewise with the copper, with any material, aluminum, and so on. So basically, in this example, you can see a lid or a light bulb, and we have a resistor. This is a physical component, a resistor, and we have a source of energy or voltage, a battery, right? Now the resistance is always impeding the flow, So if we have high voltage passing through the light, that resistor will try to impede that, reduce the voltage. If we don't have the resistor and the lid does not accept that voltage as the maximum, then you are going to burn it. So sometimes the resistor is useful to impede the high voltage. Sometimes it's not useful and causing to distort our own signal. So resistance in these physical medium like wires really depends on multiple factors. One of them, the object size. Are you using thick wire or thin wire, for example? And the length. So we have a thickness and a length. Are you using very long wire or are you using very short wire? So imagine like you have extremely long wire connecting the DRAM with the processor, for example, or with the SSD. How's that going to affect the signal that you are transmitting? You will see higher noise when you're increasing the length versus shorter cable, for example. The temperature is another very important aspect that's going to increase the noise on those voltage levels. Another thing is the material. Are you using copper? Are you using something else? All of that's going to affect the amount of resistance that we are having in those communication medium. In this example, you can see several of those metrics that impact the resistance. You can see the length, you can see the thickness, you can see the material, you can see the temperature, and you can know which is higher resistance than the other. Right? So you can see sometimes it's proportional, sometimes it's inverse proportional to the resistance. All right, back to our question, a logical question. If we decide to use a component with a VDD of 5 volts and we get through the wires 4 point something, do we consider that as a 1 or 0? Now, obviously, logically, 4 point something is close to 5, so let's consider it 1. Make everyone's life fair, right? But how about 1.2? How about 2.2? How about 3.2? What is the threshold that we should use over here? Now, it makes sense to use a range of values for the 1 and another range for the 0, because there is no way to assume an ideal situation that the 1 would remain as a 5 volt and the 0 would remain as a ground. Whenever you connect a wire, you assume always a loss in the voltage value. So it makes sense to have a range for the 1, another range for the 0. Now let's see. We are going to have an example over here. We are going to have what we call as a driver, which is basically transmitter. So we are transmitting signal, electrical signal or a voltage from one point to another point. And we have here a receiver. So a transmitter and receiver, and we have over here a physical medium communicating that voltage. Remember, we are always having a resistance in a wire that's causing to distort the voltage level. Now, if we receive 5 volts in one side, we may expect something around 4 or something the other side. To solve that issue, we consider this point. Let's maybe have a pen. We consider this exact point as output of the transmitter. We consider this point as the input of the receiver. What does that mean? It means now we will have the output in the beginning and the input last. So don't get confused. This is a really important topic. When we say output in the beginning, doesn't mean the output of this. When we say the input over here, doesn't mean the input over here. So don't get confused. The output of the transmitter going to the input of the receiver. And it makes sense. Now, we have the voltage value, or the voltage range for us is always going from somewhere from the ground all the way to VDD. VDD is the maximum voltage that we have in that component, that particular component. Could be DRAM, could be SSD, could be CPU, and so on. And we said the VDD is variable. It's something that we set up based on the component that we have. So it could be 3, it could be 5, it could be 10, whatever it should be given to you. So we have always the value from 0 all the way to VDD. Now, since we know that the noise is going to distort our voltage level, meaning that if we have a 5 as voltage input coming from here, like 5 volt or VDD basically, with the noise coming through this physical medium, the value received over here would be something less than the 5. Less than the 5, not more, less than the 5. For that, we always say the range for the output should be less than the range for the input. The range for the output should be less than the range for the input. And it makes sense because there is always added noise is going to decrease the voltage level. So if we send a signal somewhere over here, for example, this is maybe it could be 4.8 maybe, or 6, right? Less than VDD. We expect to receive that signal as maybe 4, right? Because there's a noise added to it. We reduce that voltage level, and then we might receive the signal as 4 over here. And that's why this range, this is shaded area, it makes sense to us. Okay? Now, in the low voltage, it's a different story. It's opposite. When we send a value of 0 from one side to another, a 0 cannot be sent as a 0 because otherwise we cannot differentiate it from no data at all. So if there is no data, it's still connected, and we always have a ground over here connected. So sometimes we will send something as a low voltage, like just 0.3, for example, or 0.6, right? Now, with the noise added to the low voltage, we will expect an increase in the voltage level, with the noise, okay? And that increase will enforce us to increase the range for the low voltage at the receiver side. So we'll have here higher range than what we have in the output. And over here, we also have higher range than what we have in the input. Hopefully, this is 100% clear to you.
So, Professor Naeem here, question, right?
Yes, go
What
ahead.
happens when there is a signal in between VOH and VOL, like exactly in between?
Excellent, excellent. So now it depends on how we define the ranges. And that range is not like really something we invent out of nowhere. It really depends on the transistor that we are using. There are 4 major types of transistor, and those transistors coming with a predefined shaded area. So those shaded area is ours, is something coming from the manufacturer who manufactured the transistor itself. And they are going to tell you, my circuit, the one I design, I know everything about it. I will tell you what are those values. Okay, if anything coming in between, it's not recognizable.
Yeah, there is no
That-
gray area. Yeah. I mean, the question
That will
is,
go to the forbidden zone, which is not defined, just what we call as steady state or undefined state in the logic. It's not 1, it's not 0. Is it clear?
clear. Yeah.
All right. Now I know it's getting messy with all these drawing. Let's erase and have again the important things. Remember, we call this output. Oops. Let's choose the pen. We call this as output, and this is the input. That's why we have output first, input second. Okay. Now the range over here will be smaller than the range over there. The range over here will be smaller than the other range.
I have a question.
Now, yes, please go ahead.
Is it possible for like an output to be within the range, but then it goes to the forbidden zone?
Yes, yes, yes. We will see an example of that. That's
Okay.
excellent question. So your colleague asked, is it possible to have an output over here in one of the ranges and then it goes to the forbidden zone? Yes, that's possible. How that could happen? There are two cases. Either, remember, what caused that voltage to drop to this level is what we call as a resistance. So the resistance in this wire is causing that voltage to drop significantly more than expected and causing it to fall outside this range. That's one case. The other case is to use different transistor from different manufacturer. So if you use different transistor type over here than the transistor level over there, and then you will have a collision in the requirement of each of those transistors. Okay? That's excellent point. Is it clear?
Yeah, that's good. Thank you.
All right. Now let's go back to our story and let's give it a formal definition. Remember, the boundaries of those ranges are defined by those values. Although I choose pen, but keep switching to automatic. All right. So we define this, which is the minimum level of the boundary of that range, as voltage output high. And then voltage output low. Remember, output here means the beginning of the transmission. That's what we call output. It's not the output of the circuit. Don't get confused with it. It doesn't matter what you have in here. It could be really complex circuit, doing AND, XOR, NAND, I don't care. The moment I transmit, that's my output. The moment I receive, that's my input. Now, the boundaries over here, we call it voltage input high, voltage input low. Okay? The difference between voltage output high and voltage input high, we call it noise margin high. Likewise in here, noise margin low. Okay? In order to guarantee your circuit is working well in tandem, there is orchestration, there is nice synchronization, they understand each other, you always need to guarantee that the noise margin high is greater than 0. Meaning that this range should be always accommodating this plus a noise margin higher than this range. Likewise in here, in order to design your receiver, the transistor type that you are using over there should really accommodate the transistor characteristics of this side. Is it clear? All right, I spent so much time here, but this is really important moving forward. All right, let's erase and move on. Now there's something we call as DC transfer characteristics. Let's see, what is it? This is called transfer characteristic as it describes the relationship between the input and output voltages. Let's see how. Again, the same example, we have a simple circuit called a buffer, just passing or reconstructing the input. So ideally, Whenever we say like the input is 0, the output is 0. The input is 1, the output is 1. As simple as that. No magic, just a buffer, right? And that's why we represent it. If I ask you to draw the DC transfer characteristics, it's just a relationship between the input and output. You have the input in one side, you have the output in one side. Whenever we have the input as 0, the output is 0, right? Because it's just a buffer. When the output is 1, for example, here at this scale is 1, the input is 1, then the output is 1 over here. So that's why we have it in this level. That's ideal. That's what we have in DC characteristics. In not ideal situation, which is a real life, what we will have is this way. Why we have it this way? Because always those circuits are not perfect, and it needs time to generate the output. When you send an input, you don't expect to get the output right away. When you change the voltage, you change it gradually, and that gradually will cause the output to gradually change from one state to another. That's one thing. The second thing, the gate itself takes some time to generate the output. So when you send the input this way, you change it now from 0 to 1, it will take some time for the output to get produced. And that time is defined by this curve. So you see the curve will saturate at some point, and then it will be 1. And this is what we will have in real life. Now, you don't need to remember this, and when I ask you in the exam to describe an AND gate or write the truth table, you don't really need to care about those noise or these margins. Okay, just give me 1 or 0. That's the output. But this is what we have in real life, basically. So if you are curious and you connect a wire to voltmeter, for example, you'd like to measure the resistance of it, or you'd like to measure the voltage and so on, if you have analog oscillator to connect, then you will see this shape, but you will not see a perfect rectangular shape. All right. Now, we talked about this topic already several times, and this is something we call VDD scaling, and this is something nice that we have over time. This is not something old. This is not old science. As we move with the years, we will remain in that VD scaling. Scaling means we are always going down. We never go up. With the old PC, old computers, they have a huge VDD. Now, when we shrink the transistor, we are making it smaller, then it cannot afford high voltage. And we always need to go with low voltage in order to not burn these transistors. So whenever we shrink the transistor, we reduce the VDD with us. That's why you can see the scaling is going from 3.3 to 2.5 to 1 volt, sometimes less than 1 volt in today's computers. Now, there is a saying, which is funny. It says, any chip operate because they contain magic smoke. Operate because they contain a magic smoke. If the magic smoke is let out, the chip stops working. Okay, what does that mean? It means if you observe the smoke, this is really what's happening. Okay, so you already burned that chip. So don't let ever the smoke coming out of the chip. And in fact, one of the reasons why that smoke might coming could be the high voltage or the requirement of the chip are not met. Now back to the excellent 2 questions I received in the previous 2 slides. This is the answer. In real life, we have 4 types of transistor. There are other types, but these are the prominent types of transistors. Okay, TTL and CMOS, and then we have low voltage TTL and low voltage CMOS circuits. Now, these things are given to us. These are given to us, really given to us. So you don't need to calculate them yourself. You don't need to think about the ranges we discuss and so on. Let's see. The VDD are those values. the VDD are those values. And sometimes we have different type of transistors, so you might have a range, but normally we consider this is the value for VDD. And then we have voltage input low, voltage input high, voltage output low, voltage output high. Don't ever get confused with the output and input in here. They are a different story than the gates. The output is always to the right side, the input to the left side. No, here's different. This is the output, it means the transmission or the transmitter, and the input is the receiver side. Now, if I ask you a question, can we connect a TTL, for example, to CMOS? Can we connect a CMOS to low voltage TTL? For example, I have two circuits. One of them is manufactured using different type of transistor than the other circuit. Can we connect them together? Do they understand each other? Let's see. Here I have an example for a TTL followed by low voltage CMOS transistor. You can think about this as a whole circuit. This is not just a buffer, and this is another whole circuit. Okay. Now let's see if we really meet the requirement for the physics or not. Back to our story. Remember, this is extremely important. Let's go with a pen. This is the output. This is the input. The output is over here. The input is over there. Okay, we have the voltage output high, the voltage output low. We have the voltage input high, the voltage input low. Now you just need to go through the question or the table or whatever given to you. It could be a data sheet. If you check this transistor level, you will see something we call as a data sheet. This data sheet, we call it as a white paper or a manual or documentation coming from the company. And what you would see in this data sheet, the VDD, which is 5. So they have the TTL over here. So the VDD over here is 5. Let's start filling all the values. Now, since this is the TTL, so we have output, we don't have input. So we'd be using only these things. Don't get confused with the input. We're not using it. So this is transmitter side. Now the high is 2.4. So we have here 2.4. Okay. The low is 0.4. The ground is a ground, is always 0. We don't need to think about it. Doesn't matter which transistor we are using. Now we go back to the receiver side. We have the VDD. What is the VDD? The receiver side is of type low voltage CMOS, which is this guy. What is the VDD over here? 3.3. So we have here 3.3. And in fact, this figure should go a little bit down. So we have different VDD now. So it should be somewhere in here, 3.3. Okay, but remember that. Imagine this. Now in voltage input high, we are now focusing on this guy. Don't get confused. Voltage input high over here is 1.8. And a voltage input low is this guy, 0.9. And the ground remains ground, 0. Now we want to know if they are compatible with each other or not. They are compatible with each other or not. How we know that? Remember, the noise margin should always be greater than 0 for the high and for the low. Let's see. Now, the 2.4 and the 1.8, what is the noise margin? We don't care about VDD.
It's 0.6.
Excellent. 0.6. Does it meet the requirement? Yes. It's greater than 0, then we are fine. Okay, so the noise margin, we have an enough noise margin to detour the signal from one side to another. Let's go to the noise margin low. 0.4 and 0.9. We have enough noise margin. And enough here is greater than 0. So is the difference between them greater than 0? Yes, it's 0.5, right? And this is telling us, answering the 2 questions I received, that, yeah, I can connect TTL transistor or a circuit of type TTL to another circuit of type low voltage CMOS. Okay? Do you have any question? But now in the book, there's one of the sections, you will see another table will tell you which of those types is compatible with the other type. And there are some of those types are really having more restriction on the VDD because they are low voltage. If you connect them after high voltage, it might get burned. So just if you are curious, you can check that table. Okay. What is the time now? I don't see the time. What is the time? Oh, it's 11:17. All right. Yeah, we're going slow today. Yeah, but it doesn't matter. As long as you understand everything, I clear all doubts, everything is clear to you, I'm fine.
Question, can you hear me?
Yes, go ahead.
Isn't it always the best to keep using the same transistors though?
Sorry, cannot hear well.
Isn't it best to keep using the same transistors?
Does it depend on?
Isn't it best to keep using the same transistors?
Oh yeah, definitely. Thank you, Alex. It's really recommended to use the same transistor type. However, this is not the scenario all the time because you might get really different components from different manufacturers. So you just need to deal with it, right? As simple as that. But it will be best if you get like all decent technology, all decent logic. That would be amazing. Anna, I guess you have a question?
So was the answer to that question you had on the slide yes, because the difference between the lower was greater than 0?
Yes, definitely. So the requirement that we have, noise margin high should be greater than 0, noise margin low should be greater than 0. It means like, frankly, if the circuit support more noise added to the input signal or not. If we have more noise margin, higher noise margin, it means like we allow for a noise to be added to the signal, then the one would remain 1. It doesn't matter if the one dropped from this voltage to this voltage, it's still defined as a 1. The moment we go to the forbidden zone, done. Nobody can understand what you are saying. You are sending 1, but they receive it as 0 or as a 1 or as something else or as somewhere in the middle. Does that answer your question?
Yeah, I kind of just half understand it. The question, can we have TTL logic followed by that logic? How do you know if you're going into the forbidden zone if the high is always going to be?
Oh, I see what you mean. Yeah, that's a good point. But in reality, you know the resistance, how much it's going to impact the voltage by some equation. And in that particular case, which is a corner case of the general case, yeah, we can know really if that voltage will drop outside the range or not. But in general, if you allow for that noise margin to be higher than this, then we accept it.
Okay.
And in fact, like the resistance is always impacting the voltage with small value. You don't expect like the 5 volt to drop to 1 volt because of the wire. It's not going to happen. The resistance is always small. And when we talk about PC or computer, the distance from one component to another is really short. But that's really excellent point. I get what you mean. So we don't care about the value itself because this is not given to you in the question. We never say if the input is this much of voltage and assume the noise is added by this much, then is it acceptable or not? In this case, yeah, we have more information than we can assume whether the voltage will drop really off cliff or it's going just smallly get impacted or something like that. We don't know these things. That's excellent point. All right. Okay. This is another important topic, but we can keep it until a next lecture on Wednesday. Hopefully it will be in person. So let's assume it by default will be in person, even if I didn't send an announcement. I think the GSU campus is open today, but there is still some ice outside, and that's why I decided to have it online. I don't want any of you to get hurt. Maybe we can invest now the remaining time. I know you might have lecture at 11:30, so maybe we can have this time as office hour. I'm going to stop the recording just to give you more freedom to ask whatever you like.